button. And I want to go right back to where we were in our last non-programming lecture, learning about number system. So the last slide down there was binary. I started teaching us a new number system. We, as humans, 10 fingers, we use base 10. So every number that we build in decimal, another name for base 10, has 10 digits total for every place. 0 through 9, that's 10 digits. And so we can build up any string of digits using those, and that gives us decimal numbers. But binary is special. It only has 2 digits. It's base 2. Zeros and ones build up every number in binary. And so we learned about a bit. A bit was a single binary digit and a binary number. And a byte is 8 bits. So just some string of 8 ones and zeros, that is a byte. All right? So with that in mind, I want to teach you how to convert. If I give you a binary number, remember I'm going to use those subscripts to say I'm working in binary versus working in decimal. So yeah, remember I'm going to use those subscripts. Let me show you how to convert from binary to decimal. And it's actually the same as converting from decimal to all the different places like we learned about in elementary school. So do you remember that, like, if your teacher put 1,234 in front of you, you first learned to do like, oh, that's 1,000 plus 200 plus 30 plus 4, right? And then maybe once you got to middle school and learned about powers, you could break that down further. You could be like, okay, this number is 1 times 10 to the 3 plus 2 times 10 squared plus 3 times 10 to the first plus 4 times, you can still put a 10 there, but 10 to the zeros place, that's the ones place. Look at where, this is a decimal number we're breaking down, look at where the base appears. You see that? That exact rule of breaking down numbers with that power expansion, that base expansion, works just as well for binary. So this number, whatever it is, it's definitely not 10,010. What is this in decimal? Well, we can break it down in the same way. What is this place? This is 0 times, usually go from right to left, right? This is 0 times, way over here. This is the 2 to the zeros place. See how that was 10 to the zeros place for this one? This is the 2 to the zeros place if we're working in binary. And then, all right, what's the next one? This is 1 times 2 to the ones place. Times 2 to the 1 plus 0 times the 2 squareds place. I guess I don't need these zeros, but I'm including them for fun. And this would be 0 times the 2 to the thirds place, 2 cubes place, plus one more digit. This is 1 times 2 to the 4th. You see, I'm following that same pattern. It works. It's going to work. 1 times 2 to the 4th, which is, of course, just pick the ones out. That's 1 times 2 to the 4th plus 1 times 2 to the 1st, which is 2, 4, 8, 16, plus 2, so 18. This number, 10010 in binary, was the number 18 in decimal. So you can expand it. Just use 2's instead of 10's. Same pattern. Any questions about that? Not too horrible, right? So, I don't know. Let me give you this as a screenshot really quick. You can do this. You don't have to type this anywhere, but help each other, all the people next to you. Say hello, and please work on this one. What is 1111 in binary? What's that converted to decimal? See if you can follow this pattern. This is the biggest 4-bit number, right? What would it be in decimal? The number system that we understand as humans. Try to convert it. I'll give you a couple minutes. You don't have to write it down. Just get an answer. And I'll check it with you in a second. Oh, question over there, yeah. Yeah. Oh, it's lowercase. Everything's lowercase. Okay. So we weren't answer here? No, you don't have to write it down. Paper, in your mind. What would it be? Remember to start with the right most digit. Here. Plenty of computers in this row, though. You could have sat at. But yeah, these are very large screens. I wish there was a way. Some rooms just have the computers go under the desk if you don't need them. Let's see, how's my timer? 10 more seconds to work on it on your own. Alright, that is my timer. Any brave souls want to share their answer?
What? If you do the multiplication, if you add 2, if you multiply it 2 times, multiply it 4 times, you get 16. And then if you add the 2, and then you get 18 for the left side.
So that's for this one, but I asked about this one.
Oh.
Anybody else? What do we get? Any brave souls? It's Monday, I understand. Alright, so this is how we break it down. We work with the rightmost digit first. This is going to be a 1 times how much this power of this base contributes. It's going to be 2, because that's the base we're working in, and then it's times 2 to the 0, because that's always the rightmost digits. The base to the zeros place. And then we have the next digit. We have 1 times 2 to the first, plus another 1 times 2 squared for that one, plus another 1 times 2 cubed for this one, which becomes 8 plus 4 plus 2 plus 1. So the largest 4-bit number you can make is 15. This is the number 15 in decimal. Any questions about how I broke that down? Is that what we got secretly, but we're afraid to talk and say? I hope so. Because that's the easy direction. Converting from binary to decimal is the easy way. Converting from decimal to binary is the hard way. So that's the one I want to teach you now. All right? Let's do that. So decimal to binary is much more difficult, unfortunately. So it requires you to take the repeated, like a bunch of remainders. It requires you to divide numbers and also remember their remainders after doing that division. All right? So let's pick a symbol for how to do that. Those of you who are talking, can you please just talk on Discord or something? I can't think when I hear voices. Thank you. All right, so let's talk about remainders. Here's a symbol for doing remainders. So if we remember from grade school, like here's a number, 123. Let's divide it by like 10 or something. I get 12 left over, right? Or 12 is the answer, and then remainder 3. Remember that from like elementary school? It's unfortunate that we have to go all the way back. But like there's a division result, and then there's a remainder result. All right, so remember that. And so if I just want the remainder, if I just want the 3 after doing this division, here's the symbol that I'm going to use to represent that. This is going to work in Python, so that's why I'm teaching it to you now. 123% sign 10 is going to compute the remainder after dividing by 10, so it'll give 3 back. All right, this is called the modulus operation. So this is how I want you to read it. So pretend to do division, pretend to divide 123 by 10, and then that's going to give back the remainder, not the actual division result. All right, so that's what the percent sign means. It's called the modulus operation. I'll say mod for short, so 123 mod 10. Okay, that's how that's going to work. And so again, we could do a pattern that's going to work for decimal, and it will apply to binary. All right, so that's where I'm going with this. Here is a question that you probably have never pondered. How can we take like a decimal number, a normal decimal number, and then do math to extract every digit from it in a certain order? All right, so like here's 123. How do I extract the 3? How do I extract the 2? How do I extract the 1? And like get every piece of it out. So here's the trick. I kind of showed it to you here. You can always get the rightmost digit of any number by dividing by 10 and taking the remainder. See? If you do 123 mod, or divide by 10, you get 12 left over, and then 12 is the answer, and then 3 is the remainder. So that'll always give you your rightmost digit. get that remainder, do this modulus by 10 operation. Okay? So that'll get me the 3, and then if I know how to get the rightmost digit of any number, I just need to like chop off the 3 and translate 123 into 12, because then I can get its rightmost digit and then play that game all over and over again. So how do I transform 123 into 12? Well, we can do division again. So divide by 10 and take the part that wasn't the remainder. Don't put any decimal places, just take the part that was not the remainder. And then that's going to be the pattern. That's how we can extract all the decimal digits from a decimal number. And this is eventually going to apply to binary. Okay, I promise. So let me show you this. 123, and I would like to extract all the digits of 123. Pretend I didn't know the number. All right. The first step is to get its rightmost digit by doing mod 10. So divide by 10. It goes in 12 times with 3 left over. So that gives me my 3. And then, all right, I got the rightmost digit of this number. I want to chop off that 3 now so that I can do and get the rightmost digit of the rest of the number. So I can do division by 10, and then it's like 12.3 is the answer, but chop off the decimal places. No remainders. Throw away the remainder. So just get the 12. Do you see how that pattern of doing those two things, throw away remainder, will give us all of the digits of this number one by one, just in reverse order? And now I have the 12. I can do mod 10. It goes in once, and with 2 left over, that gives me my 2. Now I can extract the 2. I can chop it off of 12 by dividing by 10. 12 divide by 10, throw away the remainder. That gives me 1. And then, all right, let's extract all the decimal digits of 1. Let's do 1 divided by 10, get the remainder, 1 mod 10. Well, it goes in 0 times with 1 left over. There's my digit. I want to chop off the 1 now, so I will divide it by 10. Throw away the remainder, it goes in 0 times, right? It's too small. And this is the algorithm. Once you hit 0, you have extracted all the digits. Then you can stop. It's like a computer. And then every time you took a modulus operation, in reverse order, you got a digit out of this number. 3, 2, 1. And so that's how we can extract all of the decimal digits from a decimal number, okay? Does this make enough sense to us? I haven't even talked about binary yet. Does this idea make enough sense? Shaking heads. Any questions that would help it make sense? Sure. This operation? Yeah. This is the modulus operation. It's getting the remainder after dividing by 10. That's what I'm going to use that as. It's a slash with some extra stuff. So that's what I mean by that. Take the remainder after dividing by 10, because you get 3 left over when you do that one. Sure, let's do another one. Let's do 4, 5, 6. Or just 45 or something. 45. I want to extract all the digits of 45. So I want to take the 4 out and the 5 out separately. So to get the rightmost digit, because you can only get the rightmost digit, I'm going to do mod 10. That will give me the 5, because it goes in 4 times with 5 left over when you divide 45 by 10. And then I want to chop off the 5. I'll do division by 10 and throw away the remainder. That gives me 4.5, but I'm throwing away the remainder. That gives me my 4. I can extract the 4. Now I have a smaller number to extract all the digits from. I can do mod 10 to get the rightmost digit of that. It goes in 0 times with 4 left over. So there's another digit out of the number. Now I want to shift away the 4, chop it off. So I'll do divide by 10, throw away the remainder. It goes in 0 times. I'm done. Now every time I took a modulus, I have gotten a digit. Every time I took a remainder. In reverse order, though. So there's the 4 and there's my 5. Does that help? All right. So what if I told you that this works for binary, converting a decimal number to binary? Do you see where the decimalness is in this algorithm? I think it's right here. I'm doing everything with 10s. If I replace these 10s with 2s, I will get a binary number as a result. I will extract binary digits. I'll extract bits rather than decimal digits. All right? So here it is. This is the secret. Just do this pattern again. Just change 10 to 2. You extract digits with mod 2. You shift away, cross off bits with divide by 2, and throw away remainder. All right? So let's convert 8 in decimal to something in binary. Here's the trick. It's just, all right, what's the rightmost bit of 8 in binary? I'm going to do mod 2. I'm going to get the remainder after dividing by 2. It goes in cleanly with 0 left over. So the rightmost digit of 8 is a 0 in binary. And then I want to chop off this 0 from the binary encoding of 8. So I'm going to divide 8 by 2 and throw away any remainders. Throw away any decimal places. So this goes in cleanly, so I get a 4. And now I want to convert 4 to binary. Extract all of its bits. So 4 mod 2. I'll go a bit faster now. That's even, so the answer is 0 left over. Now I want to chop off that 0 out of 4, so I'm going to divide 4 by 2, throw away any decimal places. There aren't any anyways. And so now I have 2 to work with, 2 to convert to binary. I'll do 2 mod 2 to get its rightmost digit in binary form. Well, that's a 0 because it goes in cleanly. And then I want to chop off that 0 off of the 2's binary representation, so I'll do 2 divided by 2, throw away remainders. I get a 1. And then finally, I want to convert 1 to binary. It's the last digit I need to extract, really. 1 mod 2. It goes in 0 times with 1 left over. That's my remainder. And then I want to chop off the 1. 1 divided by 2 gives me 0, and I have extracted every digit. So now, every time I took a modulus, every time I got a remainder, I got a digit of this number. I got a bit of this number in reverse order. So it is 1, 0, 0, 0 in binary. That is the number 8. And that makes sense. This is 2 to the zeros, 2 to the ones, 2 squares, 2 cubed, only 2, 4, 8. Right? Its own little place right there. Any questions about that? So the same pattern, just swapping 10s for 2s, extracts binary digits, bits of a number. That's pretty cool. Well, I wanted to get the 1, the 2, and the 3 out of this decimal number. That gave me the 3, the 2, and the 1. That's the same place, right? That's the same encoding. That's still decimal, 123. I want to convert this decimal number 8 to binary now. That's base 2, so I want to extract base 2 digits. That's what I mean by that. This doesn't look like 8 anymore, right? That's the goal. So I want to give you this. Here's the algorithm from the previous slide. Now you try. Try to convert 25 in decimal to binary using this pattern. All right? Help each other. See if you can do it. 25. What is that in binary? It's got a bunch of mod 2s, divide by 2s in order. And then if you have questions about the question. Yeah, we're throwing away the remainders. Everything but that. Throw away any decimal places when you're doing the division. We already used that remainder in the previous digit. And you know how to check your answer, don't you? Go the other way. See if you got it right. take another minute or so to discuss, and then I'll walk you through it. All right, we got too much to talk about today, so let's come back. I'll show you my answer, and then hopefully that will help. All right, you're going to get very fast at this, I promise. But here's how I think about it. The first step, right, it's repeatedly modulus and then take divide without using the remainder. So here we go. First step, what's the rightmost bit of 25 in binary form? I do 25 mod 2, and the trick is, the quick way of doing it is, there's always one left over if it's odd. So 25 is an odd number. I get a 1 there. And now I want to shift away the 1 out of the 25. So I want to chop it off. I'm going to do divide by 2 and throw away the remainder because I just used it already. I don't need it anymore. Throw away the decimal places. So that's 12, right? So we're chopping off the 0.5. And so now the idea is, if I can just convert 12 to binary and plop a 1 at the end, that's the answer. So now let's get the rightmost bit of 12. 12 mod 2. It's even. So it goes in cleanly, there's 0 left over. See that? Goes in 6 times with remainder 0. And then, all right, let's chop off the 0 out of the binary representation of 12. 12 divide by 2. Throw away any remainders. There aren't any this time. So 6. And so now the idea is, all right, if I can just convert 6 to binary and plop a 0 and a 1 at the end of it, I've got my final answer. So we're just making it smaller and smaller each time. All right, what's 6 in binary? What's its rightmost bit? Well, 6 mod 2 goes in cleanly, 0 left over. All right? And then let's get rid of that 0 by doing divide by 2. That's a 3. Now I want to convert 3 to binary. See, I'm getting a single digit at a time, a single bit binary digit. So 3 mod 2, that's odd, so I get a 1. Chop off the 1 by doing divide by 2. That's 1.5, but I chop off the 0.5. I'm already using it. And then let's convert 1 to binary. Very easy. 1 mod 2 equals 1. And then chop off the 1. See if there's anything left. Any other bits to extract? No. 0 goes in, and there's nothing left over. There's everything left over at that point. Okay. So every time I took a modulus, I got a digit in reverse order. So that one, that one, that one, that one, that one. Those are my digits. Apparently, 25 is 11001 in binary. Okay. Any questions about that? Do you see the pattern working? Yes. The modulus operation? Okay, yeah, so it's getting the remainder after dividing by 2. So 25 divided by 2 is, that's 12.5, but it's easier to think about it as 12 and a half, right? 12 with 1 left over, remainder 1. That's the remainder. So there's the 1. Does that make sense? And then same for the other one. If I do 12 mod 2, it goes in cleanly. It goes, if I do 12 divided by 2, that's 6. and 0 halves, right? There's nothing left over. There's no remainder. Does that make enough sense? Yeah, so it's been a while probably since we had to worry about remainders. We breezed through those, didn't we, in math class? Yeah, any other questions? You can check yourself. It's very easy to check yourself because you know how to go the other way. Here's the 1's place, the 2's place, the 4's place, 8's, 16's place. And so this is saying that 16 plus 8 plus 1, is that 25? Yeah, it sure is. So that's how you can check yourself. You can go the other way. Remember that. Okay. So definitely study this. This is a very easy question for me to ask you on a midterm. Wink, wink. Okay. With that in mind, this is just a number system. Binary is just another number system like decimal. Let me teach you how to add the binary numbers. Why not? Remember that you only get 2 digits to work with, 0 and 1. So the second you try to add 1 to 1, that's 2, but in binary, that's 1, 0, right? In binary, the number 2 is 1, 0. So you have to carry immediately. You see that? That's adding binary numbers. Again, we have 1 plus 1. That's 1, 0 in binary. 2, 1, 0. And now I have 1 plus 1 plus 1. That's 3 in binary, but that's 1, 1, right? 3 in binary is 1, 1. And so I both carry and put a little digit there. That's all you get. Zeros and ones everywhere. Again, 1 plus 1 plus 1. That's 3, but in binary, 1, 1. So that's how you add binary numbers very quickly. And of course, you can think about what this was equivalent to. This was 8 plus 4 plus 1, so 13. And we just added that to, we know what this is. This is 15. And we noticed that the answer was 28. So this must be 28 in binary. Okay? So it really is the same. It's just you have to carry a whole lot sooner because you run out of digits, which is kind of cool to think about. Yeah, that's more just for fun. I'm not going to test you on adding binary numbers. Maybe in a future CSCI class. And I just want to bring this back to why we're talking about this, because computers think in binary. That's why I'm teaching this to you. So let me show you just briefly. Again, not going to test you on this idea. It's a very complicated idea, but let me show you you can make a circuit with the things that we've been talking about to add numbers and build a computer, right? Because half of what computers do is just math. So how do our computers use these ideas, binary and logic and all these circuits, to actually do real work? So here's a secret. If you look at the exclusive OR operation, remember that from the waiter's example or something, or mom's example one day. Exclusive OR on a truth table, it's really doing 1-bit addition, because you think if 1 is true and 0 is false. What is, just pretend that exclusive OR, turn it to a plus sign. 1 plus 1 is 1, 0, but 0 is the final answer you have to carry, right? What's 1 plus 0? But 1. That's the same as true exclusive OR with false. Same with the other direction. False exclusive OR with true is still true. 0 exclusive OR, or false exclusive OR with false is false. So exclusive OR is doing 1-bit addition secretly. Ooh. And so if we combine exclusive OR to get a bit of an answer, and then also figure out if we should be carrying, we want to carry if they're both a 1, so the AND gate will give us that. We want to carry if A is a 1 and B is a 1. So suddenly we have an adding circuit. You give 2 bits to add, and we have a sum and a carry output. And you just feed those to a bigger circuit. All right, the next time you have to come around, you have 3 things potentially to add. A carry, and then your 2 bits that you originally wanted to add together. So here are your 2 bits. And you have a carry in, and you produce a carry out and a sum bit. If you just chain these things called adding circuits, these adders together, you have 32-bit addition, 4-bit addition, very, very simply in front of you, which is crazy. And so I don't want to go too far into this, but this is what computers are doing. They're just, exclusive OR gate is doing addition secretly, and it's just being chained a bunch of times with wires in all the right spots. Okay? This is a very difficult idea, but at least easy to explain. Any questions about that? That's why we're learning all this. That's what a computer is good at. We can build one now. We could, again, I'm not going to test you on making this circuit, but it's a cool idea. This is how computers add. All right, are we happy to move to a completely different topic? Rest our weary brains. All right, because the next thing that I want to talk about is more philosophical. I want to talk about privacy, and I want to talk about encryption. So there will still be some computational topics for the rest of today, but it will be through a different lens, I guess. So let's get on into it. Let's talk about privacy in this digital age that we find ourselves in, right? Because we all have computers in front of us, we all have phones in our pockets, most likely laptops as well. Just too much going on. Everything's connected. So how do we remain private? Do we even have a right to privacy? Let's think about that. All right. So at least as citizens of the U.S., we have the Fourth Amendment, and what that does is it prohibits unreasonable searches and seizures. So that's pretty strong. If somebody wants to come search your house, for example, they need a warrant from a judge and probable cause. So that's kind of nice. But the question is, what about the internet? What about stuff that you put on the internet? It's not in your house, right? It's in Google's cloud somewhere. It's in one of their servers in some desolate area of the US. So the internet's not your house. It's a different place. So does the Fourth Amendment apply there is the question. So let's look at some history. So back before the internet, we had phones, of course, still. Back in the day, the Supreme Court ruled that you did not even need a warrant to tap a phone because that's just AT&T's line outside. It's not your house. And a conversation wasn't any physical thing that you could touch and take away. So why can't let someone listen into that? They ruled that you didn't need a warrant to even tap a phone, but luckily they changed their mind in the 60s, and so that's better for us. So that's some prior rulings, but again, the internet it's a weird place. Does the law exist there? Is the next question. And so I have just a few examples to talk about the idea of privacy on the internet, and maybe that will help you discover, do we have enough? Do we have too much? Who knows? So here's a fun example from the textbook if you chose to buy it, but I will summarize it to you here. Target, probably a decade ago now, what they did is they did some early form of data mining, which is so common nowadays, like targeted ads and things like that. So what data mining is, by the way, it's just looking for patterns, pattern finding. It's machine learning. We know a lot about it now since the rise of ChatGPT and things. It's more in our lexicon, but back in the day, this was all brand new. So we were looking for patterns and things, and corporations want to look for patterns in how you buy things so they can sell you more stuff. Okay, so Target noticed that pregnant women would buy certain products at certain stages of their pregnancy, and so it's at this trimester they would buy a lot of this, at this trimester they would buy a lot of this, and Target got really good at noticing that, and they could predict when someone was pregnant sometimes, which was interesting. So they took that data that they found, linked to your credit card or something, and they sent targeted ads, which is probably the best pun I'll ever make in this class. They sent targeted coupons and ads to those women. All right? And the question is, does that infringe on their privacy? Did they have a right to privacy as they were shopping in Target? Should this data have been taken from them and used to generate ads and things? All right, so that's the question, and the answer is something I want you to come up with. I can't tell you the right answer; there is no right answer. But we can, of course, ask our boys. We can be like, all right, what would Kant say about this? He would probably ask a question with the word "always" in it. Should everyone always data mine from their customers and look into every little detail of what they're buying? He's probably for individual freedom, so I would say Kant would be against this. But again, you could probably use his words in the opposite way. And then all of the utilitarians, John Stuart Mill included, would be like, what is the utility in these ads, right? You could on one side weigh the fact that, oh, well, this is really, really taking away from someone's privacy. They're shopping and they should not have to deal with this. Nobody should be looking into their bags as they're buying things. So maybe that leans you towards no. But you could also, on the flip side, argue that, all right, if these women were going to buy this stuff anyway and they're getting coupons for it, now it's cheaper, maybe that's a good thing. So there are two sides to every coin here, and that is a fun example to ponder. Any thoughts, comments about that? Do we hear about this? It's been a while, I think. It happened at least a decade ago at this point. That's fun. Fun little idea. There's plenty more where that came from. So here's just another example. Ad blocking on the internet is something that I at least like to do. So it is not illegal to block ads. That's nice. That's why ad blockers exist. But it is technically illegal to block ad blocker detectors on certain websites. So that's a mouthful. But if you have an ad blocker, sometimes the website notices that you have the ad blocker and they're like, disable it if you would like to be here. That it is illegal to be blocking those things. And the reason that that gets shot down is that at that point you are tampering with that website's form of access control, and it's been ruled that websites have a right to control access to things that they are showing to you. Like, for example, a news website like the New York Times. If you go to it too many times and you don't have an account, it locks you out. Or if you have an ad blocker, it locks you out. They're showing you copyrighted content, right? They're showing stuff that their editors wrote and stuff like that. So they have a legal right to keep you from looking at it and trying to make money, right? And so you could ask the question, should ad blocking exist in the first place? Because maybe you're a corporation and you want people to look at these ads so that you can make money. So what is the ethicality of all of this? Is there a good reason for it or against it? And again, you could ask our boys. So this is what you should do if you're ever faced with an ethical conundrum. You would be like, all right, what would Kant say? He'd probably ask a question with the word always in it. Should we always be looking at ads? Should we always be clicking on the ones that we see? Something like that. Should we always be buying the products that are shoved in front of our faces on these websites? And so I assume Kant, again, for individual freedoms, he should be like, no, I don't think that's a good idea. He'd probably be against ads and for ad blocking. And then Mill, again, a utilitarian, would try and weigh it. Again, there's always the perspective of the person who's showing you the ads and the person who's viewing the ads. Okay, so what are the benefits? What are the pros and cons of ad blockers and ad blocking? Well, a pro of blocking ads is that you get to actually read the article that you went to the website for, and you're not distracted. So you have like more real content in front of you. So that's nice, saves you time. But on the flip side, the website that put the ads there in the first place is making less money, because if you don't see the ads, you don't download them from that ad person's server, then that website's not making money. And especially you don't have the opportunity to click on that ad, and some people do. That makes a lot of money for the person who's showing the ads. So you've taken away an income source for them, and maybe their website goes down because of it. They couldn't pay for the hosting. So that's the other side of that coin. So ad blocking, should you do it? Thoughts, comments about this? These are just a few slides to make you think. Again, there's no right answer, not at all. I just want to give you examples so that you can make an informed decision yourself. And this is the logo of uBlock, or MuBlock, I guess. If you want to install one, this is like the most popular ad blocking add-on for most browsers. Okay, so that's ad blocking. One more topic in this section. Let's talk about Google Street View. Have we ever used it before? It's pretty common, right? You want to go and like, what does the outside of my house look like? What does the outside of this business that I'm about to travel to look like so that I can turn at the right spot? I use it for that all the time. So most countries have plenty of Google Street View data, right? This is like blue. Blue means all of these streets have been mapped on Google Street View and there are pictures of them. Notice, though, that Germany is very blank. Not a lot of Google Street View data there. And even a Western European country can hold a completely different view on privacy to others, right? So, okay, Google Street View is everywhere in the Americas, over most of Europe except for Germany, because Germans don't like the idea of it. As a culture, they are more mindful of their own privacy, and they have made laws so that you could very easily, or they've made laws that make it very hard to take this Google Street View data. Like only in the big cities is it easy to do that. So that's pretty interesting. Other people don't like the idea of Street View. It's so ingrained in my mind to want it, but I could see the point. Google does let you remove or blur out your house on Street View, if you've ever heard of that. That is a possibility, even in the US. Why? It's just somebody doesn't want you to look at the outside of their house.
Maybe it's private, they're offended.
Yeah. And that's culturally, Germans have that mentality at a large scale. It's just a different thought process. Nothing wrong with it, but this should help you, like, hopefully you're rethinking your ideas about Google Street View. Like, it doesn't have to be a given that it exists. We let it happen. Should we have? Critical thinking class. All right. Any questions about any of that? Comments about this section before I move on to a different one? The last 30 minutes of class. So I want to talk about a concept called encryption, which is everywhere these days. We log in with passwords, right? We should hope that all of our internet traffic is encrypted so that nobody can steal stuff from us. So let's talk about encryption in general. It is the idea, it's the process of encoding information, translating it into something that's jumbled, and only me, the person who's sending it, and the person who's receiving it can unjumble it. That's the idea, all right? Only the parties involved, so there's a concept of like a message, that's what you're trying to send, some secret thing. Only the people that message is intended for should be allowed to decode the message that has been encoded, okay? That's the terminology. So you encode a message to encrypt it, you decode it to get back to what the original message was, right? It's all over the place. If you use any website with a password on it, it's very widely used for both security on the internet, just like you have an Instagram account. Or if you're about to buy something like commerce, you need to send your credit card information over the internet, right? And anybody who's looking in should not be allowed to read your credit card number. Okay? So that's the goal. It makes sure that does not happen. It makes sure that only your credit card number can be seen by Amazon, even though it's being sent over like Comcast's pipes from your house's internet connection. Something like that. So that's what it's all about. And so let's learn a few pieces of encryption, a very simple one and then a very hard one. You'll have to wait till CSCI 26 if you want to get good at the hard one. But here's like the world's earliest example of encryption back in the BC era. It's named after Caesar. It's called the Caesar cipher. Another word for that is ROT13 is how I'll pronounce it. And it stands for rotate. ROT stands for rotate. Rotate 13. So the idea is you have some message that you want to send to somebody, like hello, and you just rotate all of those characters 13 later in the alphabet and wrap around if you pass a Z or something. So like H turns into, apparently 13 characters later is U, and then E turns into R, and then L turns into Y, and O turns into B, and vice versa. So like hello becomes Uryib, and then you like send that to somebody on your like Greek era battlefield, and only they can decrypt it. Something like that. But it looks jumbled, right? It is very easy to unjumble it. I think it would be very easy to crack these days, but this is like a very early example of encryption. It's taking something that looks normal and making it look not normal, so that only the people who know the secret to undo it can read it, all right? One thing that's nice about the Caesar cipher is there are 26 letters of the alphabet, 13 is halfway. So if you just run the Caesar cipher again on the encrypted data, like the U turns back into an H, it wraps around. 13 letters later is the H. 13 letters after the R is the E. And so it is its own inverse, we say, which is pretty cool. Like A plus 13 is N, and N plus 13 becomes A. Pretty nice. But that is like the simplest possible encryption. Very easy to break, though. But again, it has all the features of an encryption. Makes things look jumbled unless you know the way to unjumble. Any questions about that? Have we heard of this one? All right. This is not what is being used on the internet. That would be way too easy to crack. So let's talk about what's being used on the internet. And do I have an example of that? Like, I don't know, class website. Can I stop attendance, by the way? Do that if you haven't. If you go to any website, including the class website, there's a little lock there. Connection secure. Tell me more about that, Firefox. More information. It's like, ooh, view the certificate. What is happening here? There's a lot of stuff going on. Elliptic curve, SHA-256 with RSA encryption. Cool. So it's telling me about how my traffic is safe being sent to the class website, stuff like that. Let me teach you about RSA. That's used in every website, pretty much. That's how all of your data is sent safely. All right. So in RSA, there's two things, and they're called keys. Those let you decrypt things. So there's two kinds of keys. The key to encryption is publicly available. Interesting. Anyone can send you a message using what's called your public key. All right. So if somebody wants to send you something, like here's the cloud that they're writing to you. Like I'm trying to send my password to the class website. The class website tells you its public key, and you use that to jumble your password. And so that's what you send to the class server. It tells you it's a thing called a public key, and you use that to do the encryption. Right? RSA was invented back in the 70s, and it is so foolproof that it's still in use today, just with bigger numbers involved, of course. So it's very mathematical. It's very cool. You have to wait till CSCI 26 to understand it fully. But everybody has a public key that they let other people look at if they want to send them private messages. And then they have a secret, what's called private key. So there's two keys. They have a private key that lets them decrypt the messages that were sent to them with their public key. All right, so that's the secret. So here's like the setup. I don't know. Here's you, and somebody wants to send you a message. So here's the other person who wants to send you a message. I'll call them the sender. And what they're going to do is they're going to ask you for they're going to say, I want to send you a message. And so you're going to send them your public key. You make that available on the internet. Like, all right, here you go. Send me it. Use this to encrypt. And then they're going to take their message. Let me do my best drawing of an envelope. They're going to take their message, and they're going to what's called sign it with your public key. And so now it's an encrypted, jumbled form that only you can figure out what it was saying. All right. So there it is, a message with a public key encrypted into it. And all right, then that's what they send you. And it's jumbled across the internet's pipes, which is nice. And so you are saving secretly a private key that can unlock this encryption done with your public key. This is private key. I know this is all very vague right now, but I'll give you an example in the next slide. And that's just for you. You don't show anybody this. The second you share your private key with anybody, your encryption is toast. And at the end of the day, this is just working with fancy large numbers. The reason RSA works is because the message is a big number, the keys are big numbers, and it's really hard to factor those numbers. There's some large prime numbers involved here, and they're different every time. So that's what RSA is all about. It's just a big math problem that is easy to solve if you have the private key, essentially. Okay, that's RSA in a nutshell. Look it up on Wikipedia if you're interested, because I think it's cool. But here's a simple example with much smaller numbers than are used in the wild. But RSA is about modular arithmetic, so it's about remainders again. That's why I had to teach you that also. So there's a public key, and that's a set of two numbers. So a public key, if somebody wants to send you a message is also just a number, right? Because you can encode it in binary. A public key is two numbers. We'll call those N and E. Let's pretend that this is our N and this is our E. E is prime. And then there's a private key, D. This one. And they're all, like all of these things, these three numbers, they're all generated from two giant prime numbers usually. All right? D and E are what's called modular multiplicative inverses, and you do not have to remember that term outside of this class. Don't worry, I'm just showing you this as an example. But the goal is, like, you can now send messages between people using this public key. These are just numbers in this private key. You can send messages, you can send any number, right? A message must be a number as well, between 0 and n minus 1, because that's what you get when you take a remainder after dividing by this. So you can't send the message 0 and you can't send the message 1 for reasons. If you try this, it won't work right. But you just make sure that never happens in the real world. But all right, so you have a message. You want to send something to somebody, and here's what happens. So if you have a message M, let's say, I don't know, let's say that we want to send the secret message 42 to somebody. So our message M is the number 42. Here is how you encrypt it. to encrypt M to send to somebody, you're going to use their public key. So you're going to calculate M to the power of E modulus N. So mod, that's the percent sign. This is a mathematical thing. So take the remainder after dividing by N, and that's called C. All right, so let me do that. Stopping this before I forget. I'm going to go to a language that we're going to learn in a second. If I can get my start menu. Here. There we go. Here, let me cheat and use a calculator. I'm going to use Python as a calculator. This is a programming language we're going to learn later in this class, but here's the idea. I want to calculate M, which is 42, so 42 to the power of E, which is 17. So that's that giant number. And then I want to take all that and do mod N. So modulus 3233. And I get 2557. And that's the secret value. That's the jumbled value that I send to somebody. 2557. So there's some large numbers in effect here. And we call it C because that's called ciphertext. It's like the encrypted form of the message. And you send that to somebody. And then you get it back. And then you can use your private key to decrypt it. You can calculate that ciphertext to the power of D mod N. And it undoes everything, surprisingly. It's going to give you back your original message, M. So let's do that. What's that? C is 2557. Come on. 2557 to the power of D, so 413. It's that giant number. And then you do mod N. 3233. And miraculously, we get a 42 out at the other end. Right? So that's the secret. There's a lot of fun math involved. DNA, where it's called modular multiplicative inverses. So the idea is like you take the message, you send it to the power of E, and you send that back to the power of D, that like they cancel each other, assuming you do mod N. That's equal to the original M as long as you're doing mod N arithmetic. So there's some really cool number theory involved. You'll have to wait till a more advanced CSCI or math class to fully understand it, though. But that's RSA. That's what is keeping us safe on the internet. Any questions about that?
I think it's going to be a little bit hard. I hate to say it, but I think it's going to be a little bit hard for me to write this down.
That's why I'm giving you these slides. Why would you have to write it down?
No, to understand the essay. Maybe I can talk with you about this.
Sure, yeah, I'm not sure what you mean by essay yet. So, okay, let's talk about the ethics of all this. Like, encryption exists so that we can make it so that people can't eavesdrop on our stuff, including the police or something like that. So, is it ethical to use encryption and send messages? To send messages. So here's the debate that I want us to have now. Let's get into groups, and I'm going to assign you a stance. So if we can go to the written nice page, I'll clear that out. But here's the idea. Let's have this debate now. Is it ethical to use encryption to send messages to somebody? Because that's going to make it so that it's very hard for anybody to listen in. Maybe you want somebody to listen in. All right, so I'll split you up into two groups. People who are for encryption and people who are against encryption. So remember that you can just click submit and it will give you a group number. Pick some representative. If you have an even group number, then you are for encryption. You think it is ethical. And you better give some arguments for it. If you are an odd number, group number, you are against encryption. And you need to give some reasons against it. All right? So please try to write at least two good arguments in support of your stance, either for encryption or against encryption, and then we'll come back and we'll talk about it. You have to press submit to get a group number.
What do you think? Are you
It'll take like 5 minutes for this. We got time.
click submit first?
Clicking submit will give you a group number. There you go. Following your stance, come up with some good ideas.
We're against, right? What decryption is. Should we look it up first?
we be allowed to encrypt our messages?
That means like I agree. Decryption, we should. No, no, we should not. The reason why decryption shouldn't exist. The reason decryption is no one isn't okay. Isn't okay. Decryption isn't okay. Is because let's think about it. The reason why I thought it isn't okay because one, because nothing can stay private forever. Because not all stuff is private. Because nothing can be private forever. Because you think
Oh, it's been an hour.
you think
That's funny.
you hide your private stuff, your private stuff,
Reconnect.
but they'll eventually find it. This is really not working out. Yes. Or against because I think I know why it's private. Okay, because it could really hurt someone's feelings. It could really offend someone like whatever you change to have it against others. Like that's the thing because some people promote because it could promote criminal activity.
2 more minutes to get some good stuff in. Try to get 2 good arguments for your stance.
This is what I also believe. In addition, I also believe that another reason encryption is unacceptable is that one is that they can always get into is that some people might gossip about others. This is unacceptable is that people out there will have the right to cyberbully. Yeah, that's it. The right to have free access to bully others and learn
All right, 1 more minute to get something in there, and then we'll discuss.
and get away with it. Here's another reason. In fact, they can send threats to others. They can threaten others, and they can say, "I'm going to burn down your house," or "I'm going to hurt you." In fact, they'll only they'll they'll get they'll cyberbully others, but they will also get in trouble. Okay.
3, 2, 1. All right, that is my timer. Let us come back and discuss. Let's see what we thought. Was it hard for whatever
hard.
stance, especially if it's the opposite of the stance that you had? All right, let's look at an even group and an odd group. So even using encryption is good because everyone deserves privacy. Yeah, it's all about our right to privacy. It helps because someone could try to blackmail you if they saw your messages. Good, because that would be very easy at that point. They could just look in. Same with another even group. Like no one needs to know some things about you. Like no one needs to know your credit card number. It would be very hard to have like an account because people could just keep on hacking into it. Good. All right. So that's people for encryption. Nice arguments. Let's look at some odd groups, some people against encryption. All right. It can hide things that can potentially be dangerous. That's a very standard good argument against encryption. right? If certain people have the right to access messages without encryption legally, then it is unethical to use encryption. So some people, like companies require people to have like large companies. How do I want to say this? Governments require some companies to put in like little back doors, and maybe that's what you're getting into here. That's a good thought. It's unethical because everyone should be open with one another. I like that idea. Yeah. It's a very Kantian kind of argument. We shouldn't be wanting to lie. We shouldn't want to be like talking behind someone's back. I like that very much. That's a good argument against encryption. It's unethical because it could be used to conceal malicious things. Good. So very good thoughts, everybody. Thank you for writing about that stuff. If you're ever stuck, a good idea to do would be to like ask our boys. What would Kant say? What would Mill say to all this stuff? And I don't know why that everything is frozen for me right now. That is a problem.
Maybe try restarting your computer.
It is too late for that. Let's see.
Turning it off and then powering it on.
We do not have enough time in class for that to happen.
I'm sorry.
But we will press onward one way or another. I might just have to restart PowerPoint. Give me a second. There's one thing. We always have technical difficulties, don't we? Well, it's really unhappy. That's impressive. I hope it's saved. All right.
If it's not saved, that would not be good, right?
Yeah, sorry about all this. I have one last trick that I will try. PowerPoint. Go away. Well, let's try this. When in doubt. Yay! We have certain things still. Okay, cool. It's all been saved, more or less. Awesome. So let's talk to our boys quickly. What would Kant say? What would Mill say to all this? Well, Kant... Why is this so small? I fear that by changing something, it will break again. What would Kant say to all this? He's like, all right, a question with the word always in it, usually. Kant is for individual freedoms. He's pretty much for privacy. He would be like, private info should remain private. I don't want to tell everybody my secrets. I wouldn't want anybody to like ask them of me. I'm not going to require anybody to tell me about their private stuff either. So private info should remain private. That's probably what Kant would think. Private info should remain private. He's for individual rights in that way. So that could help you get started with an argument. And then Mill would always weigh the options. You'd be like, all right, encryption is good because it helps us with privacy. We get privacy out of the deal. That's a pro. But a con would be it's harder to protect people from harm if we allow encryption. Protect people from harm. I think there's a good example of like a law enforcement agency, like they were trying to try somebody for a murder, and they had an iPhone that they couldn't unlock very easily because it's very hard to break that encryption. Or they just did it wrong. They didn't ask Apple first. But that keeps people from maybe being arrested when they should have been. Something like that. So that's stuff to think about. You can always ask your boys and weigh the options, especially for a utilitarian stance. Any questions, thoughts about that before I move on to the last topic of today? So it's just a lot of ideas thrown at you, and there's no right answer. It's interesting to have a class where there's no right answer. So, okay. A few more slides. I'm going to have to skip one just for time purposes, but you can read it if you'd like. Let's talk about 3 topics. I guess I'm going to get to 2 of them, though. They all have to do with the same idea. So the first one is about a person named Chelsea Manning. So back in 2010, so over a decade ago, she gave the website WikiLeaks, which is notorious, right, almost 1 million classified or maybe unclassified, but still very sensitive kinds of documents. They were from the military, from diplomatic things, so things that the rest of the population doesn't get access to normally. And so it was very sensitive. You're not allowed to do this. So what she did was illegal, right? But she was a whistleblower. She leaked something. So this kind of leak, like leaking almost 1 million documents, That's impossible to do before the age of the internet, right? You could not have leaked like a truckload of documents very easily otherwise, because you would have to print it all out. Now you don't. So she leaked a lot of this stuff. I think it had to do with the war in Afghanistan. Like there was some issues with civilian casualties, and there were way more than the U.S. government was talking about, something like that. You can look it up if you're interested. But she thought that it was a good idea to leak these documents, and she was sentenced to 35 years in prison for this leak. Those years were commuted by President Obama, though, so she is free right now. And so the question is, like, she found something that the government was doing wrong, in her opinion, and she wanted to inform the public. The question is, does the value of informing people about bad things outweigh the value of confidentiality? It was illegal to do this leaking. Was it a good idea? So there's an option. You got options here. You can weigh this. On one side of the coin, like it's good to keep the documents confidential even if they show some bad stuff, because confidentiality protects people. Confidentiality protects people. Let me write that better. Protects. That's one side of the coin. But also, if you leak this stuff that probably should be leaked, depending on what your viewpoints are, then once these things are out in the open, you could make a better decision as to who you're going to vote for next. Or if you're an activist thinking about these kinds of issues, then you have more firepower for your activism. So there's an upside there. So there's more info for voters who are on the fence and activists and things along those lines. So this is definitely an ethical conundrum. A lot of people think one thing, a lot of people think a completely different thing about this topic, and so that's why we're bringing it up, right? So look up Chelsea Manning if you're interested. If you were in her position, would you have done this? Would you have made this, all these documents available? Right? So that's one thing. Next was the Panama Papers, which I don't think I have enough time to talk about. It's another large, widespread leak about issues. People were doing bad things, and maybe it's for the best that this stuff got leaked. And then finally I'm going to fast forward to Edward Snowden, because that's the biggest topic to think about this with. All right, so Edward Snowden, he worked for the NSA. He leaked a bunch of documents a decade ago showing how the NSA was spying on its own citizens, on U.S. citizens. Like Facebook had backdoors, Apple had backdoors, so that people who thought they were using encrypted things, they actually weren't using encrypted things, and the U.S. could sneak in on all that stuff. And so they captured a lot of information that they were not legally allowed to capture. The NSA broke the law, all right? And so he leaked a bunch of classified documents. They were classified, showing this. And because it was against the law to do this whistleblowing and leak these documents, he was indicted for espionage, and he is currently living in Russia, evading like U.S. and U.S. allies, because they would arrest him on sight if he went to any of those countries, because he broke the law for putting all this stuff out in the open, right? The U.S. technically broke the law. He talked about it, but he broke the law himself in leaking these documents, classified things, showing that the U.S. itself was breaking the law. So there's an ethical problem there that maybe we should think about, okay? So hopefully we've heard of him. Definitely look him up, because he's going to be the topic of your next essay, all right? So this will be due week 6. Take some time to think about it, but here's your next essay. It's a short one. It's a 500-word essay. Doesn't have to be super long, so you're welcome. But here's your prompt, all right? Your prompt is, was it right for Snowden to blow the whistle on the NSA? Go and look this stuff up. Come up with an argument, either for or against. I don't care what you think, as long as you write a good argument. So that's your first question. Was it right for Snowden to have done this? Do you agree with what he did? Also, do we have a right to privacy on the internet? That's a public place. It's a public utility. Like, if I use PG&E, they know they're hooking in, and they're telling me exactly how much power I'm using in the hot month of August, and they're asking me to pay for it. Nobody cares about that. Why should we care about privacy on the internet? All right. So here's your prompt. Respond to that in at least 500 words. I don't care about the stance you take, but you better talk about both sides, because that's how you write a good argument. You have to bash one down if you think a different one. You don't have to write about Kantianism or utilitarianism, but you might want to. It might help you. And then finally, I want you to cite one source in your essay, at least one source. So I do require a citation for this, all right? The one thing you're not allowed to cite, as usual, is Wikipedia. Just go to the links that Wikipedia is citing, right? Go read those. That's what I want. So I'll mark you down if you cite Wikipedia. That's the one thing you're not allowed to cite, okay? But any citation style is fine. I don't care. You can use MLA, APA, whatever. And there is a programming language to write essays that I don't remember if I talked about before. So if you want a challenge, use that. But that is your next essay. Are there any questions about it? Due week 6, and apparently the real due date is September 12th. Okay? So you got a while. Any questions about any of that? If we're good, that's all I got.
So it's September